DimStiller is a tool for dimensional analysis and reduction. We use it to analyze a dataset generated from an environmental sustainability simulation. We create a new expression which prompts us to load an input file. The new expression is added to the expression tree. Expanding it shows a detailed list of the operators in the expression. The file input operator gives us details such as how many points and how many dimensions. Here we have 5,000 points and 294 dimensions. DimStiller provides workflows to help users reuse useful expression patterns. We choose the Reduce PCA workflow. The individual steps are listed here, and we add the operators to the expression. The first operator, covariance, is already active. When we select it, its operator control becomes visible. We see a scree plot with the operator's input dimensions ordered by increasing variance. We click log scaling to get a better view of the low-valued variances. Selecting a dimension in the scree plot culls the dimensions to its left. Expanding the operator in the expression tree shows the list of culled dimensions. We click the Step Operator button to move to the next analysis stage. The Data Normalize operator normalizes each dimension to the same range to remove bias in downstream computations. Collecting together the highly correlated dimensions reduces the number of output dimensions. The matrix shows pairwise relationships with a diverging color map, where red is negative, yellow is uncorrelated, and blue means positive. Decreasing the threshold gathers more dimensions together. The new matrix view reflects this change. We see the output dimensionality of the operator decrease from 147 to 23. We can see which original dimensions have been collected together in the expression tree. The next step is the Reduce Principal Components Analysis operator. This scree plot shows the eigenvalues of the principal component dimensions sorted by magnitude. We click on the scree plot at 16 where the eigenvalues taper off. In the expression tree, we can see the coefficients of the input dimensions that were used to create the new dimensions. The final View SPLOM operator draws a scatterplot matrix with linked highlighting between the plots. We have now loaded a computational chemistry dataset to evaluate a given clustering. It has 47,000 points and 30 dimensions, one of which indicates cluster membership. We choose the third workflow, Cluster Verify. The first attrib color operator allows the user to pick which dimension should color the points. We choose the dimension called Cluster and select Categorical Coloring. We color the 236 clusters with a repeating palette of 10 visually distinguishable colors. We step twice. The PCA scree plot shows a distinct knee in the eigenvalues at dimension 3. We select it to cull the rest. The new principal component dimensions segment the input dimensions into 3 mostly disjoint groups, as we can see from the names. The scatterplot matrix shows that the spatial structure does not seem to correlate well with coloring by clusters. To check whether this observation is just an artifact, we return to the upstream color operator to permute the coloring. After clicking a few times, we still find that the cluster assignment does not fully reflect the spatial patterns.